Gauss's law in integral form can be written as E dot ds, where this integral is over a surface S, equals Q by epsilon naught, where Q is the charge contained in the volume which is bounded by the surface S. If we assume that this law holds true in any dimension and consider the case of one-dimensional space, so we are considering the case of one-dimensional space, and we are assuming that we have a charged particle Q sitting at the origin, and suppose we take a volume element of length 2r. This is our volume V, which is simply an interval of length 2r in one-dimensional space. This volume has a surface which consists of simply 2 points A and B. So in one-dimensional space, this integral over the surface is replaced by sum over these 2 points, because the surface is simply a discrete set consisting of points A and B. Since electric field, the magnitude of the electric field depends on the distance, and the direction of the electric field for points to the right of Q is towards right, and for points to the left of Q, direction of electric field is towards left, and the direction of this area element at point B, since the direction of area element is outward pointing from the volume element, so the direction of this area element is same as the direction of electric field at B as well as at A. Therefore, if we evaluate E dot ds at point B, it will simply be the magnitude of the electric field at point B. Similarly, if we evaluate E dot ds at point A, it will simply be equal to the magnitude of the electric field at A, and since magnitude depends only on the distance r, so it will be the same as the value of E dot ds at B. So if we take sum of E dot ds for both of these points A and B, we will get 2er. So we are taking sum of E dot ds for point A as well as point B, and we'll get 2er. And by Gauss's law, this must be equal to Q over epsilon naught. So our electric field will be, the magnitude of the electric field at a distance r from this charged particle Q will be Q over 2 epsilon naught. So as we can see, the magnitude of the electric field in one-dimensional space is independent of the distance from the charged particle. No matter how far away we go from this charged particle, the magnitude of the electric field will remain the same. Even if we go infinitely far away from the charged particle, it will still be the same, Q by 2 epsilon naught.